Very good. Thank you for the introduction and actually for the invitation. I really like to, yeah, I really like this topic, although I was doing mostly nowcasting in the last years, but this is something that I also really like to share. Hopefully I can give you some nice message about dual polarization capabilities from weather radars. What can they bring in and what cannot? And also I would like to thank my colleagues for helping me on building the presentation. Um, So I'll just paste the abstract here so in case you want to read it again, because I think this will be recorded so you could take a look later on. But some key messages or keywords here is weather radars, dual polarization variables. So I will introduce what dual polarization variables are. And something important is the data quality that could impact the estimation of rainfall rate. Um, and then I will start then with the first motivation. So weather radars are a very useful tool, a remote sensing tool to monitor severe weather events like tornadoes or related with severe wind gusts or hail damage, or also extreme precipitation, estimation of extreme precipitation. So there has been a lot of effort from the weather radar community to improve the data quality from those weather radars. And with that, I would like to just to as a warm up to show you how a weather radar do the scanning and how it obtains the data from the surroundings. So it pretty much it rotates the antenna 360 degrees at a specific elevation angle, and then it moves up in elevation in order to obtain a 3D volumetric picture of the system. As you see, as you go, as the antenna goes up, then you are seeing the top part of the storms, and that's why you see less in the projection in the X1 plane. And one key word as well from this animation is the along the beam, the radar will sampling in range, and the resolution is called the resolution volume. And from some time, this resolution volume has been from 1 kilometer size and is decreasing. So we have more resolution in space. And I believe now we have weather radars with 125 meters sampling range. So I think that's also good news. Um, okay, let's then move to what does a radar does actually. So it sends a sequence of pulses, and it waits, and it hears what object is in front or around it. And with that time, then the radar knows the location of the storm and also how many particles are there. So what the radar actually measures is power. It doesn't measure rain directly, but it just measures the power back from the scatters that crosses the path of the beam. Okay, so what we do is that we normalize this power in order to obtain reflectivity, and this is probably something that maybe hopefully most of you hear about this word of reflectivity. Anyways, I will come back to that in a moment. And maybe this is a good motivation. Why dual polarization? So actually the raindrops are not as you see on the left panel, but actually the shape of the raindrops are most similar to the ones that you see in the top panel, because as they grow in size, they also tend to oblate or to get wider in the, let's say, in the x-axis. And because of this shape of the drop, it triggers the motivation um, to obtain or to send the pulse in two polarizations in the horizontal plane. So let's say, oh, sorry, in the horizontal plane, the XY, so you will have a wave that will be sensitive to the cross section of the drop in the XY plane horizontally. But you also will send and receive vertical echoes that are more sensitive in the Y vertical plane. So in this case, in the YZ plane. So you will have no one signal that tells me about the size in the horizontal plane, but you will have two, and those are perpendicular. And that's what is called dual polarization. So you get signals in both in the horizontal and in the vertical plane. And this will just trigger so many variables. Well, not so many, but a few variables that we could add to the original conventional reflectivity variable that I mentioned before. So reflectivity is, I say again, is converted from power, so it's in units of dB, or normally it says dBz. But the new one that we have that I can show you today is the differential reflectivity, and also called as ZDR. What is this? So as I say, you have power in the horizontal channel. Do you see my mouse, by the way? Can you see my mouse? Okay, good. So if you see, the ZDR is defined as the difference between the powers, or the reflectivity in the horizontal and the vertical. And this is the what we call a ZDR, or differential reflectivity. If we assume that a drop has this shape, then we will have more power in the horizontal than in the vertical, and therefore we will have values of ZDR larger than 0. In this example, then you have in the left panel the reflectivity going from more or less 0 to, differential reflectivity, reflectivity going from -10 to 60 or 70 dBz. In the right panel, then you see the differential reflectivity, and then it goes a bit smaller, so it goes from 0 to 5 or 0 to 6 dBs. And then you see which areas you have a region of bigger drops, and which areas you have a region of smaller drops. So you have a drop that is small and is spherical, then the differential reflectivity will be 0, right? Because both the power will be mostly identical in the horizontal and in the vertical axis. So that's for liquid. So what happens when you have ice or solid precipitation? Then the ZDR values doesn't go from 0 to 8 or 0 to 6, but actually goes from -1 to 1 dBs. So it goes in a very small range. But it also is helpful because then we can have, for example, reflectivity and ZDR. And with two variables, we could tell a bit more if it's rain or if it's solid, or if it is a solid particle like gravel or hail. I will get back to this classification later on in the slides, but I just wanted to bring that up. So the next variable, so we have reflectivity, differential reflectivity, and a third one is the differential phase. So you measure differential phase. What is this differential phase coming from? As I said before, you have two signals that you send, one that is more sensitive to horizontal and the other one to the vertical. If there is nothing surrounding the radar, so the two signals will travel parallel to each other. There's no delay from one to each other. But in the moment you have objects along the path, so you have precipitation area, then because assuming that the raindrop shape are those like you see here on the top right, so the horizontal will slow down a bit compared to the vertical signal. So there will be a delay, a phase difference. And that's what we call differential phase difference. So here's an example of at the beginning, there's no object, so the two signals are on top of each other. And as the echo or the radar signal travels along the path, then you'll see a start increasing of this differential phase because you have, again, two signals. A visualization of this. So if the x-axis here, we call it the range, and the y-axis is the differential phase. It's actually an accumulation differential phase. As you move away from the radar in range, then this differential phase starts growing from 0, let's say, to 10, 20, 50. And if there is an area, noted by the green rectangle, there is an area of rain, then you will have a much faster increase of this accumulation differential phase. But it's quite hard to really use this accumulation number. So what we actually are interested is on the specific differential phase, which is the derivative of the differential phase in range. So and this is the equation that it denotes KDP. So we actually just call it KDP, or specific differential phase. And because it's a derivative of VDP, units is given in degrees per kilometers. Remember that the VDP is given in units of degrees because it's a differential phase. So the KDP will have units of degrees per kilometers, and it will tell me how quickly the differential phase is growing or is accumulated in range. As a quick example, I will show you, for example, this is the path of along the rain beam of the radar. And then you see VDP. Well, sorry, CDP, VDP. I will explain why the difference later on, but let's assume this is the same differential phase I was talking about. And for the first 10 kilometers, there's no difference. So because there's nothing in between, so that's the difference between the two phases is 0 degrees. And then you see a first group of raindrops, and then the differential phase increases from 0 to 20. Then it continues to be 20, and there's another region increases by 50 degrees. So we have 70 degrees. It continues to 70, and then there's a third region right in the back, and there's not too much rain, so it only increases by 10 degrees. And then you have the location, right? The range of these raindrops. And then you could obtain the derivative, and that's KDP. So the first range from 10 to 15, the derivative is 0. Then the differential phase increases from 0 to 20, so the derivative is 2. I is divided by 2, by the way. And then and so on. So you get a more, a better feeling of, the number of drops, or the presence of raindrops in this area, in those three areas. And you see that how the derivative, so how quickly the differential phase increases, is given by this number of KDP. And then you have a profile of KDP from 0 to 0, then 5. So in 5 is there has been a lot of presence of raindrops. And so the KDP is a measure of how many they are and how oblate they are, pretty much. This is what KDP means. Okay, so that was my example, just to give a bit more of insight of what this specific differential phase variable is. On the top, you see this accumulation pattern. So the radar is in the middle. So the differential phase is 0 degrees. And as long as you move away from the radar, then you see there's areas of precipitation. And then you see that the differential phases start to accumulate or increase in range from 0 to 70 degrees. If you take the derivative, then you see a much better map, which localizes in which areas, and azimuth sectors, you have more liquids, more raindrops, bigger raindrops, and they are more, the concentration also increases. That's why you have values of KDP as high as 6, 8, or 12 degrees per kilometer. So why I'm talking about so much about KDP, the reason is if you do some scattering, one second, let me take this away. Yeah, if you take a relation, a empirical relation at X-band frequency, for example, between KDP, so this is specific differential phase, and rainfall rate here on the X-axis, then you see a pretty linear relationship, and that's pretty wishable. That's very advantage, I think, for us in order to estimate rain rate from KDP. Normally, we used to use the reflectivity on the y-axis here in the bottom plot, but you see that the relation is not so linear as it is for the KDP. So that's one advantage. Wait a second. Yeah. So that's the first advantage. The second advantage is that this KDP is not power dependent because it's just the difference of phases. So the power of the signals could decrease, but the differential phase remains the same. It's not affected by how much raindrops are along the path, along the beam. So it's independent of attenuation, but also independent of calibration, because again, we're not talking about dBs where there's no power. This is pretty much the phase. So that's what KDP is. So yeah, it has these qualities. Another variable that is very related to KDP or to the differential phase is this term A, which is in units of dBs per kilometers. And this is the specific attenuation. So you could also obtain the specific attenuation from the differential phase, which is again independent of calibration and power attenuation. I will also talk a little bit more about these two variables, so this specific differential phase. So let's move to the third or fourth variable, polarimetric variable, is the copolar correlation coefficient. So correlation coefficient is a correlation number, so it goes from 0 to 1. And let's see an example. So what it means is that it indicates the relation between the horizontal and the vertical size of a group of hydrometeors, so of a group of particles in this resolution volume. So it tells me a little bit about how diverse are the particles within a resolution volume or within an area. It decreases with increasing oblateness. So if it's spherical, you will have a very high correlation, so values of 1, for example. When you increase the oblateness of the randomness of the orientation of the particles within an area, then this correlation coefficient will also decrease. And again, it's also useful to distinguish raindrops from other hydrometeors, so from solid precipitation, or from non-meteorological echoes. So for example, ground clutter or biological clutters. So again, it should be very high, really close to 1 in case we have, for example, spherical particles, because the symmetry in the horizontal and the vertical is pretty much okay. It's very high symmetrical. Once you have the shape of the particles start changing and they also changing orientation, the correlation will decrease. So an example here, you see a PPI of this autocorrelation variable. This is a radar that is very close to the coastline. You see here more or less the coastline here. And again, you see here values of this correlation coefficient below 0.8, for example. Then you see that this is not rain. This is something. It's an echo, but it's not rain. What you see here is actually a wind farms. So we have information about those echoes, but this is not rain or no hydrometeor particles. And that's where the values of the correlation coefficient drops. Actually, it drops quite fast. Anything below 0.9, pretty much, we can assume it is not a hydrometeor particle. It could be useful again to remove because this is pretty much clutter, right? So what we want is to keep areas of autocorrelation coefficient more larger than 0.9, 0.95. Just to give a feeling of the range in which we want to use this copolar correlation coefficient. That was my last introduction of the polarimetric variables. And now, now we can move to what can we do now with this KDP, reflectivity, differential reflectivity, and correlation coefficient. There is a chain that we need to follow more or less, and this is more or less the order that we normally do for the quality control of weather radar echoes. And we start with the clutter identification and clutter removal, right? Then we also like to estimate to process this differential phase, no? As I said before, to take the derivative in range, because then we could obtain KDP, zones of high areas of precipitation. We also need to correct reflectivity for power attenuation, because again, at C-band frequencies, X-band frequencies, there's loss of power, and therefore attenuation is significant. We also want to know about the classification of hydrometers, so we could also use polarimetric variables for that. And at the end, I think what we are more interested in is to estimate QPE or rainfall estimation, and we could use all these corrected polarimetric variables in order to also estimate rainfall rate. So let's start with before I jump into the clutter removal, good news for us is that we have a very nice open source weather radar community in which we share a lot of articles that show algorithms in the articles. They are also shared among the community in order to apply, for example, few of those processing that I just mentioned. So we could actually, we don't need to start from scratch. There's always options to start working on this chain in order to improve the data quality of radar data. Okay, now let's move to the first step. We have clutter filtering. And then we have, for example, in the left panel, we see a lot of ground echoes and sea clutter echoes. And on the right panel is after applying the filtering. What you do here is actually you use non-polarimetric and polarimetric variables. So for example, the reflectivity, the variability of reflectivity, the gradient of reflectivity and different elevation cuts, as I said before, the radar could do a scanning at different elevations. So you could obtain a vertical gradient. And of course, the velocity. If there's a clutter and it's not moving, then the velocity, the Doppler velocity is 0. So you could also use this information to detect areas of clutter and remove them. On top of that, you also have texture from the differential reflectivity. We could also have texture from the differential phase. the KDP, for example, and of course the correlation coefficient. As I said before, anything that is below zero 0.9 probably is no weather radar echo. And the way to combine this is using fuzzy logic. That's mostly the most conventional way to apply this, is to use this using a fuzzy logic method, and then you could remove to a high percentage some unwished areas of non-precipitation echoes. As I said before, attenuation correction. So the signal loses power as long when it moves away from the radar, and you see reflectivity and differential reflectivity in this example. And after attenuation correction, then you see how much power you lost. But the good news is that we have differential phase again, which is independent of calibration and attenuation. And you could obtain a PIA. PIA means the path integrated attenuation. So if you have the reflectivity, for example, here, which is attenuated, you obtain PIA, then you can obtain the attenuated corrected reflectivity. And that's what you see here in these two plots. So you need to again process the differential phase that I mentioned before, which is this accumulated variable. And you can obtain this by doing some basic processing to remove some noise. And then you obtain this PIA value. Here's an example. So on the green box, you see the differential phase, a bit noisy. Well, it's always noisy, differential phase. That's the disadvantage of this variable. After applying a quite basic filter, then you could have the VDP. And then with some easy parametrization, you can obtain the PIA. So this is on the right bottom panel. You obtain PIA that goes, for example, here from 0 to 10. And if you add this PIA guy, to the reflectivity, then you see, for example, how this profile of reflectivity increases more or less when you go up beyond 5 kilometers. That's where you see the power difference. But you could correct this using this PIA. And you could do the same for the differential reflectivity. So this is a way to correct power measurements like reflectivity and differential reflectivity using attenuation correction and a ray by ray. So you do this ray by ray, and then you close the circle using the differential phase map. So this is one quite very advantage of the differential phase to estimate reflectivity. Another application could be to classify different hydrometeors particles. So you have heavy rain, you have light rain, but you also can have solid precipitation like graupel, snow, hail. Okay, and so how can we distinguish one from the other? Again, you could use again a fuzzy logic approach in order to avoid fixed tertials. That's the advantage of fuzzy logic, or also a clustering, a bit more fancy way to do it. And you could again use the polarimetric variables that I mentioned, and maybe also include temperature. Temperature could also help in order to distinguish solid precipitation from liquid precipitation. And this is an example of identifying more than 6 different hydrometeor types using a fuzzy logic approach. This is quite nice because then you could actually estimate rainfall rate in areas where it's rain. And areas where there's no rain, well, then you have to replace your methods to estimate QPE. Next one, this is a cool example. The radar could also detect, as I say, solid precipitation or hail in this case. And if we verify with hail reports from the Met Office mobile app, then we can obtain a very nice map which correlates the location of hail reports with the product from the weather radar itself. Moving to another, mostly the most interesting application for the community, for OpenSense community, is to estimate how much precipitation it falls to the ground. And then you have, for example, on the left panel, different empirical relations obtained from the dysdrometer 10 series. So using this dysdrometer, and you simulate variables like reflectivity, differential reflectivity, KDP, or specific attenuation, as well as rainfall rate, you could obtain a very nice plot, a scatter plot, and you could see more or less, you could fit these empirical relations to derive rainfall rate from these variables. What shouldn't surprise you is that top right is the less narrow or the most wider scatter relation because it's reflectivity and rainfall rate. In the middle is the KDP and rainfall rate, and you see a very nice narrow correlation when you have high values of precipitation. And the estimation is actually quite less noisy than the previous of rainfall and KDP. Then you have a mostly narrow relationship between rainfall rate and specific attenuation. So these last two variables, KDP and A, are potential variables in order to estimate rainfall rate. This is a seedbed frequency and a temperature of 20 degrees. Why I said 20 degrees? Because it has been shown that there is some sensitivity on the temperature in order to do this fitting. So if we want to use a specific attenuation, for example, we need to help a bit the method in order to minimize the impact of temperature for the fitting relationships. And actually what I like is that we have now more than one variable in order to estimate rainfall rate. So we have reflectivity, KDP, and specific attenuation. The recommendation is when you have high values of reflectivity, so about more than 35, 40 dBz, then this is in the moment in which you want to apply the RA relation or the RKDP. Below this threshold, and after correction of reflectivity, then it's okay to use the RZ relationship. So this is more or less the recipe in order to derive rainfall rate estimation. I think probably you already are familiar with the flooding event that happened 3 years ago in July 2021 between Germany and the Netherlands, Belgium, Luxembourg. And so we did also some comparison from different retrievals of rainfall rate, and we compare it with rain gauges. So what you see here is 24 hours rainfall accumulation retrievals. Retrievals from, for example, in this first panel, you have the only reflectivity, and then you estimate rainfall rate. So we have the RZ relationship. In the second panel, you have a combination of reflectivity and the KDP, and you see a bit of an increase of precipitation. Then you could also do the same, but now using KDP and a specific attenuation, and it also gives me more values of rainfall rate. So apparently, as this method sometimes leads to underestimation of precipitation. However, radars cannot really scan precipitation very close near the surface. And as you move away from the radar, then the vertical gap increases. Lucky enough, we have in this area, the west part of Germany, we have a polarimetry X-band radar. And we also used the data from this radar in order to sort of fill the gap. And then you see that using the radar data from the X-band radar, the map of rainfall rate increases even more. And then you see if you take the rain gauges in this area and you combine it with, you plot against the accumulation from the rainfall estimation using the specific attenuation KDP, you see a very good relationship. But before of that, the relationship was not so good. So this case was actually pretty interesting because it have a lot of developing of precipitation at low altitudes, and that's when most of the time the radars underestimate the precipitation. But rain gauges could help for sure, or a gap filler as well. Moving to my last. Okay, now to almost finish my presentation. How many minutes do I have left before my 20 minutes reaches?
Basically none. But
Basically none.
yeah.
Okay, sorry for that. So there's good news. Again, the variables like attenuation and specific differential phase help us to mitigate beam blockages problems and calibration problems that affect reflectivity. The limitation remains that everything is a good story before we reach the melting layer. The moment the radar beam reaches or crosses the melting layer, then there is a lot of issues and limitations, as well as the very noisy characteristics of this differential phase, We have interference from other mobile of radar frequency that also impact the quality of the radar data, as well as the vertical gap. And the vertical gap, again, is, I think, opportunity for using opportunistic sensors like rain gauges and CMLs. Well, just to emphasize that there's an open source radar community. Use it, please, and also the operational weather radar best practices will help us a lot to take the good path towards a good rainfall estimation. And with that, I finish my presentations, and I leave also the reference that I use and good literature review for people that wants to get involved in weather radar processing. Thank you very much.
Thank you, Ricardo, for the presentation. And now we have like 5 minutes for questions. If anyone in the audience raises a hand, they can ask. Or the chat is also open for questions. If there is none,
I believe this is the very first.
yeah.
Sorry,
I hear someone. Remco.
Hello.
Hey, good morning, everybody, and thanks, Ricardo, for your excellent overview. Question: you mentioned this vertical gap, right, between the radar sampling volume and the ground, where, of course, for most applications, the main interest is. I was wondering about the horizontal gap, thinking about radar networking. We experience, of course, still the fact that in radar networks, like in Opera, you see quite some differences between the way in which different meteorological services process their data. And of course, you have the range effects that you also refer to. And of course, that is an issue for many of the applications, typically in hydrology, because river catchments do not stop at country borders. So, well, thanks for adding this additional slide. It looks like we prepared this question, but I'm sure you'll be able to give your perspective on this.
Yes. Thank you, Renko, for the question. I think it's also a very important aspect to pay attention to, because indeed, the more radar we have and the more overlapping areas we have, actually, it helps us to minimize or to increase the fidelity of the quality of the radar data. So one disadvantage actually is when you move or you observe echoes at far ranges, the resolution, the resolution along the range is the same, but it opens up. So you have a very wide cone, and that's not good. So what you want to have is actually use observations from a neighboring radar sensor, and that could help us to minimize this widening of the radar sampling. Again, you mentioned a good point for different ways to calibrate, to process, but maybe the differential phase is the one that could help us to avoid some kind of those issues coming from different weather met offices that maybe they have their own unique processing chain. So KDP specific attenuation could be one of our friend in order to do composite of rainfall rate, for instance. Thank you for the question again.
Thanks, Ricardo. The vertical gap remains, of course, right, between the radar sampling volume and the ground.
Yeah, that's something that we cannot do much because then if we lower the tilt, then we just get most ground clutter echoes. There's ways to minimize this, but no, we cannot do too much about it. We got lucky. We have a collocated X-band radar, but there's no everywhere X-band radars, and so. But thankfully, we have telecommunication antennas, which could help us a lot, and also rain gauges, which I think Thomas will tell us a bit more about the potential usage of rain gauges.
Excellent, thanks.
Yeah.
We still have a place for one question, if there is any. I can ask. One of your last slide was about challenges and limitations, and that leads me to a question: what future enhancements you expect in weather radar technology? to mitigate those challenges and limitations?
So for example, for the interference, once you have the moments, so when you have KDP and reflectivity, you cannot filter those anymore. I mean, you could filter, but then you will lose a lot of areas. You will remove rain as well, so you don't want to remove those areas of rain. But if you take a look at the spectrum signature, so in the spectral domain, before you integrate to obtain one value of reflectivity, that's the moment in which you could see the contribution of different echoes from different frequencies. So you see in the spectral domain the signature of rain, for example, and the signature of a radio frequency. So you can filter this, and then you integrate, then you have a reflectivity, which is less contaminated, but is interference. So that's more or less a processing methodology that you could do in the spectral domain, so before you integrate. And for the for parametrization, DSD variability, maybe some blurring, I think now the doors are opening for methods like machine learning, in which you could also train a network in order to avoid this fixed parametrization, ABC parameters that we always use. So I think that's more or less what I would like to say before. I don't want to move to phase array, but that's also another way to go.
Okay, thank you.
Thank you.
Thank you, Anna.
Perfect, thank you.
And thank you also, Ricardo, for paving the floor in the topic of radar. That was a really good talk, so that I don't speak so much about radar and I can concentrate on different topics in my speech. So what I'm going to present is some work about comparing radar data and precipitation ground values and differences that we see between rain gauges and IoT sensors. So before you can compare radar data to rain gauge data, radar data have been corrected, as Ricardo explained, but rain gauge data, they are not always the truth. On the one hand, they are, of course, only point measurements, and within the footprint of one radar volume, you can have quite some variation when rainfall is coming to the ground. And therefore, it is important to quality control rain gauges also in real time. And what we are proposing is to start from simple to complex issues. So when we receive rain gauge data, we are recognizing missing values so that they are not used. They are flagged, and we eliminate values that are outside the physical range. So sometimes you have transmission errors and you have then, for example, negative rainfall, and this, of course, needs to be eliminated. You cannot work with this. Then we are checking for outliers on different time resolutions. And these are usually 1 minute, 5 minutes, 60 minutes, and 1 day. And sometimes you can have other transmission errors where you are having, for example, a factor of 10 in the data. And with this, you could recognize this if these values are very high. The next check is a neighborhood check. And we compare with stations in 4 directions. And we are looking if the value of the station that we are examining has too low values. So if in the 4 directions you have values which are considerably higher. For example, if the middle station has 0 millimeters and all around you have 5 millimeters, both seen within 1 hour, for example, then these 0 millimeters can be considered as being false, or at least they are not corresponding to their neighborhood. You can also do this for too high values. So if the station that is examined has a very high value, then you can look around, but you have to be more careful here, since convective rainfall can be very localized. So your high value in the center of your 5 stations may in reality be correct value. And so you have to be very careful when you are applying this, or you need to know that your rainfall is not convective at all. Then this could help. What is also possible is an internal check. That means at one site, you are not comparing with neighboring stations, but with other parameters. For example, if you compare rainfall with sunshine duration, and if you have got 1 hour where you have 10 millimeters of rainfall, and you have 60 minutes of sunshine, then you know one of the two is not right. And finally, what can also be done for controlling rain gauges is using radar data. And this is something which currently is under development at our company. And for example, when it comes to 0 values, or when it comes to values where you have got one high value which is suspicious, you can check with radar data, and you can very often find a clear answer whether the value can be used or should not be used. And stations with remarks on these checks, they are excluded from further processing, at least for the time for which they are suspicious. It does not mean that the values really are bad, but when we are in a real-time setting, we need to be sure only to work with those data that we are confident with. I will not go very much further into quality control for rain gauges in real time here, because I would then shift over to sensors that we have been using. However, rain gauges are most often used as reference, and they should only be used as reference when they are quality controlled. And so these quality control steps, they are most relevant for adjustment of radar data in real time, what is quite often being done, in particular if you do not have all these dual pole data available that Ricardo told about. So we have a project where we are using an IoT rain sensor. Here you can see the sensor. It is an optical sensor, and this is the solar panel. And it is working with infrared technology. and we connected it to the LoRaWAN network in Lübeck, and we have in Lübeck 50 stations of this kind, and there are another 50 stations in Bochum, in Hagen, and in Lüdenscheid. And what we are using these data for is, on the one hand, we compare to radar data, and a project partner is trying to use this for AI-based forecasting. The data will be published at the end of the project. So first step was we wanted to find out what we can see with the sensor, or what the sensor can see when it is seeing drops. And so we went into a laboratory. We had precise device to drop onto the sensor. And we tested the sensor. Well, as a matter of fact, we tested 3 different sensors to compare with 3 different rainfall amounts in a given time. And we did this with 2 different setups. On the one hand, we wanted to see the role of a drift, wind drift, and inclination. So the simulated wind influence when the raindrops are not falling vertically on the device, and the role of the drop location on the measurement cone. And what we could see is that we had higher variability in particular in the lower classes. So this sensor is offering us 7 rainfall classes, which were not further specified. And so we tried to find out what it means. And one message is that we have differences between the different sensors. And we have an intensity level which is increasing with increasing inclination. The sensitivity is variable for different locations on the cone. And a quantification in terms of intensity of all the levels 0 to 7 is difficult because it gives you a wide range of uncertainty. However, we thought there should be something for which it is useful, and therefore we compared the sensor levels also with rainfall intensities from radar. And we had two questions, and this is coming back to the vertical gap that Ricardo talked about. Where does precipitation seen by radar hit the ground, and when does precipitation seen by radar hit the ground? And we calculated statistics based on correlation. So how does it look like? We are having the sensors here as black dots. And when they are measuring something which is not 0, then they are getting a different color. And we are having radar data, adjusted radar data with the ordinary rain gauge network. And so we try to put the color scale more or less into the same region. And then we compared what we can see. So this is one event as an example. And you can see how the rainfall with 1 square kilometer and every 5 minutes is coming up from the southeast. And you can see that some of the sensors are reacting and they are reacting in similar colors as the radar intensity is giving. But some of the sensors are also giving a different intensity than the radar. And so the question is, why is it? Is it a problem with the sensor? Is it because the radar sees the rainfall earlier than the sensor, because the rainfall still has to fall down to the ground, or whether there is drift in the rainfall so that the location where the radar sees the rainfall is different than the location where the rainfall is touching the ground. So what we did is we looked around and we shifted the time series for each of these events and for each of these sensors. So we have, for example, two time series. The black line is a time series of the sensor, and the blue columns are the rainfall values from the radar. And when we shift the timestamp by 5 minutes, so that the sensor is shifted to the left, then we can see that the correlation is going up. And we did this for each of the sensors and for each of the events that we looked at. These were events of this summer, 2024. And so we got an impression that we needed to shift most of the sensors by 5 minutes for most of the events. So we came to this conclusion when we overlaid the overall rainfall amount, which you can see in the radar data, with the degree of correlation that we reached at each of the sensors. And so here you can see that we have good correlation in this area, while we have relatively bad correlation along these outer parts where we have less rainfall on the one hand, but where we are also on the side of the event. And we still need to analyze whether this is also connected with the travel speed and direction of the rainfall cell. So we had these 5 events. And for the events, we then found out if we are looking at the same timestamp between sensors and radar, we are getting for event 1 a significantly worse result than with the sensors 5 minutes later. And this is for event 2, not as pronounced, but also visible. Here it is not really a difference. Event 4 is not very different either, and neither event 5. We still need to look more into that. On the other hand, what we did, we shifted the location of the radar by 1 kilometer into each direction, to the north, to the northeast, and so on. And so we could find out that for one of the sensors, we did this for each of the sensors. For this sensor here, we have for the co-located correlation, we have around 62 63% correlation, and a correlation factor of nearly 75 when we are going 1 pixel to the north. And we did this for all of the sensors. And if we have a uniform uniform picture, then we assume that the rainfall as seen by the radar really reached the ground 1 pixel further. This is still ongoing analysis on these 5 events. So as a conclusion, we investigated IoT sensors based on infrared technology to detect precipitation around the year, and they are able to do this. These sensors are far from providing precise or even quantitative measurements, but they are useful for a comparison between radar values taken aloft and the detection of rainfall occurrence on the ground. Here with 5 events, but we will look into more of them. And we have seen a clear temporal shift with high rainfall intensities. And we have also seen cases of a spatial shift. And so we need to look further into where really the rainfall that we see by the radar is reaching the ground. And here, such simple devices can in any case help. And we are going on with further correlation analysis towards a 3D correlation cube so that we can see in time and in space where the rainfall occurrences are deviating and where they are best fitting. Well, with this, I am ready for questions and for further discussion.
Yeah, thank you for your presentation. We definitely have some time for questions. So if anyone in the audience, you can just speak up or raise your hand. The chat is also open for questions.
I have a question.
Hello, good morning.
Hi, morning. I'm Juliana from Germany too. Thank you for the presentation. It was very interesting. I would like to know which product is used for the radar. Is it a composite? It's a local product. Is there a difference from the range if the time shift is always 5 minutes, or if you go further from a radar station, it would be larger?
Well, here we analyzed the data in Lübeck. And so this is a local radar that where we produced a 1 kilometer grid product. So it is 1 radar. And of course, there will be a difference as function of the distance from the radar, because the measurement will be higher up as at a longer distance. And what other questions did you have?
Not that this were both one. Thank you.
Thomas, could you elaborate on how the radar is adjusted? Because you have these levels of intensity, right? So I guess that the radar data also have been adjusted, maybe against some ground measurements.
Yes, they are adjusted against the gauge network of the German Weather Service, which is not very dense in the area of Lübeck. It is denser, well, because we are using other data there than in the other 3 cities that are equipped with the sensors.
Mm. But it could be that, you know, that adjustment, because you select those, was it 7 categories?
Yeah.
That one is just a bit off and then end up in one
No,
category.
we did not adjust to the sensors.
Okay.
We just compared.
Yeah. Yes. Yeah. Okay.
The values of the sensors, they were really too random sometimes.
Okay. Interesting. Thank you.
Jochen is raising his hand.
Yes, thank you, Thomas, for this interesting talk. I have 2 questions. One is these sensors that detect rainfall. What happens if it stops and the sensor is wet? Does it still detect rainfall, like this sort of wet antenna attenuation that we have with the CMLs? So is there maybe more information about the duration of the event than actually was happening?
The sensors are remaining still wet for roughly 5 minutes.
Okay. And they still record rainfall for that period?
Yes.
If you check it in the lab. Okay.
Yeah.
Okay. And the other question is, if you shift your correlation in time and also the rainfall field, do you have some physical evidence if this is like reasonable, if you know the beam height of the radar and above ground and make some assumption about the fall velocity? Does that justify that sort of 5-minute offset? Or is it sort of contradicting this a bit? Or are you looking into this if your time shift and your vertical shift, horizontal shift is sort of physically plausible given the wind directions and the fall velocities?
We still have to look into this more in detail. My colleague is still learning quite a number of things, but 5 minutes shift in time seems to be plausible. It could also be 7 or 8, as my other colleague has observed on other occasions when he compared to rain gauges. Because when you are doing adjustment with rain gauges, you also need to take into account that you have some travel time between the upper part and when it's coming down. But what we usually do not consider is spatial drift when we are doing adjustment, because we simply do not have enough knowledge on that.
Okay. All right. Thank you.
Thank you. And I don't see any other question. So, Maarten, yeah, we can hear you.
Yes, hello, Maarten Reyniers from RMI Belgium. Do you see any advantage of these sensors over low-cost tipping buckets? Is it the robustness? Is it the cost? Or is it just another sensor that is being tested? So I'm wondering if there are use cases for these sensors that are not possible with normal tipping buckets.
Well, you do not have any maintenance on these sensors. And that was one of the reasons why the project decided to go for these sensors. And so they are a first try. I never saw them before. And so they are try what we can do with it, what they are useful for. And well, as usual, the manufacturer said they are measurement devices, which is quite a bit doubtful. But you can see something which is more than just wet and dry.
Yes. Okay.
But for quantitative use, I think low-cost tipping buckets would be better in case you have the required maintenance that you can do.
Okay, thank you.
You're welcome.
Yeah, thank you for the discussion. I don't see any more questions. So I guess we can close the meeting for today. and we can already invite you for the next meeting, which will be on 26th of November, again Tuesdays at 9.
Yeah, maybe if there are questions coming up later, either on these low-cost sensors or on quality control of rain gauges, which was relatively short, please feel free to contact me.